Okay, good evening. So in this tutorial today we'll see how we can lay out a CMOS inverter. As you can see in the left we have a schematic where we have a PMOS and NMOS. You might be noticing that we have 4 terminals. Since we are doing layout, now we need to go to exact implementation of these transistors. So you might be familiar with the gate, source and drain. We also have a body contact, and similarly we have both for NMOS and PMOS. So in the implementation in the CMOS process, we have a P substrate in which we have all our NMOS devices. As we can see this NMOS, we have in the P substrate, we have these N plus and N plus are source and drains of NMOS, and this P plus is used for biasing the substrate. Similarly for PMOS, we have P plus source and drain and NMOS as body, but we have a separate N well in which we have made the PMOS because we need an N base for having to make a MOSFET. So why this is important, we'll see like in the layout, we'll see where we need to put this body contacts, N wells, and this N plus contact for the PMOS. So we'll start with now with a simple, we'll first start with a schematic of an inverter. We'll use so now again we'll use the technology library N18. This is NMOS. We'll use 1 micro. For PMOS, so here the length is the distance between the source and drain, and the width is, if you see, since it's a cross-sectional view, yeah. Hello. Yeah, fine. So this length is the distance between the source and drain, and width is something which is just if you see inside the screen. So here we have taken length and width. Now we will just quickly connect. Now we'll label some number names. This is output, input, VDD, and ground. This is our body contact. Now we'll use a supply from analog lib. So we have two options. Either we can short these two nets, or we can label exactly the same this VDD. So when we label two nets with the same name, it just shorts itself. Let me use one. To give an input, we will use V pulse just to generate a square wave. 1.8. This is the levels. Now we need a time period. We'll give 1 millisecond. This is a basic structure of our inverter. Now I will do a transient analysis. We will add to the output both input and output. Now if we see these plots, so it's a the waveform is, this is bottom one is input and output. So our inverter is working properly. Now we'll cover like for making layout we need to create a symbol. Symbol is something equivalent to what we have in any coding language, programming language. We have functions. Like if even if you have 10 functions or 10 or 100 of lines of code, that function can be called using a single one statement. So similarly, we will make a symbol out of this so that that can be used for our further for, we can go ahead with the layout. I'll save this. Now to create a symbol out of this, we will remove all our ideal components. I only have our transistors, or in case of some analog circuit will have resistors and capacitors. So now we need to add a pin. Pin is like in programming language we pass a parameters. Similarly here we'll need a pin. So for pin we need to press P. So that will create a pin. So let's keep it now. Let's give a name VDD ground INPOUT. So we can connect here also, or otherwise we can simply place here. So what it happens, since this out and this out are same, so it is that it is shorted. So now, so we have for our schematic we have four input terminals. Now to how to make a symbol, we'll go to create cell view from cell view, then press OK. Now this will create a object. We need to put like where we need to put this ports pins. So let's keep the VDD on top. We will shift down. In the left, we will put the input. So when we press OK, so this type of symbol is generated. So that's it. We will save. Now, what is inside this symbol is we can find it by pressing equal to sign on our keyboard. So when we press equal to, it will switch between the two modes, the schematic view and the symbol view. Fine. So now if we see in our inverter, we'll have schematic as well as symbol view is there. So when you open symbol view, it is our top view, and if you open schematic, So this is our inverter. Now how to simulate with symbol. So what we will do is I will make a new cell view. I'll give the name inverter underscore TB test bench, and I will call from this inverter, since whatever symbol we have made, now we can instant it. And again, for there is a shortcut like click on the symbol and press space, so all the terminals will be connected, and the name of all the pins will be given to a net. Now again we will need our VDC. This is a good way to give biases. That it is floating, it's fine. Now we'll run. Error. So if we go inside, so this is our, I can check last time when we were quitting it was not saved properly. If you want to go inside, we just double click and enter, and to come out you need to press Ctrl and E. Now, just run it. So we can see that we have similar results. Actually, whatever inverter we had with PMOS and NMOS now is inside this symbol. So whenever we want to go inside, we can press Shift E or double click and Control E to just come out. So this helps us to, if we have a big circuit design, so we can like in programming, if we have a very large coding programming, we can break it into small modules. Similarly, in circuit design, we break it in small modules known as symbols. Now we are interested in making the symbol, the layout of this inverter. So now we'll open the uh, schematic of this symbol and we'll start with the layout. So for that, first we need to go on inverter. We'll open the schematic where we have pins as well as our components. Make sure you don't have any ideal components because we cannot lay out any ideal components. Go to launch and layout Excel. The first step to start the layout is whatever a schematic you want to make, click on it. create new, press OK, and again. So this is the place where we lay out something, we'll do something similar what we have on the slide on the right. So now we have again, similarly, as we have instantiated our transistor, similarly we can instantiate the transistor, but now we will have the layout view. We can press I and we can exactly see like whatever transistors are there. Press enter and you need to press shift F to see the inside layer. So this is a simple NMOS transistor which we have instantiated. These are our source and drain. What we are seeing is the top view. This is our side view. The N plus 2N plus is similar to this uh, this part, uh, and this gate, our gate is this one in blue. Gate are made using poly, and these are diffusions source, and this is drain, and this is gate, and this is active. This whole part is the active area. So this is one way like we can instantiate similar to, we need to always set equal width and length. Based on that we can instantiate. One other way is there is one option here. You can see it is written generate all from source. When you click this, whatever is there in this schematic, similar the layout view will come in your layout editor. I will ignore this IO and PR. I'm only interested in instances right now. If you press OK. So now if we click on the PMOS, this gets highlighted. If you click on NMOS, this gets highlighted. So this is the good advantage. Like whenever you have any module, it gets connected and we can easily we can easily instantiate all in just one click. So now we are interested in connecting the drain of these two transistors. As you can see in the inverter, the drain of two are connected. Source is connected to VDD and one source, PMOS, NMOS source is connected to ground. Why the name source and drain is like it is the source of charge. In PMOS, it is the holes are the source which flows from source. Always the current will flow from source to drain. So in PMOS, from source, hole will transfer to our from source to drain. In NMOS, electrons will transfer from source to drain. So the current flows opposite to the flow of electrons. So that's why drain is on top and source is on bottom. For PMOS is like this. Now what we'll do is we need to connect the drain of these two, PMOS and NMOS. For now we'll zoom it further and see. This is our drain. You can see the out is labeled and here we have out and this is ground. So what we will do is, now if you can see that the grid is pretty big. If I want, I'm not able to, you can see the jump between the small yellow box. So now first what we will do, based on our, we can set the grid size. When we press E, so what we can do, we can just reduce it 10 times. So while reducing it 10 times, now we can have smooth, we can draw any we can draw any rectangle. The we can have very smooth movement of this drawing. So one way is, these are the layers on the left which we can draw. You can see that these are made from P type material. This is N-well and P strip. There are many layers. Even connecting these drain to drain or source is through wires. So that wires, we in this process we have 6 metal layers. So metal 1, metal 2. So there are various layers we need to draw. So what UMC has provided, they have provided a complete transistor. So we don't need to draw it everything from scratch, making separate source, drain, well, gate, all those connections. So now, so these transistors are made. So what we are more interested now is these NMOS and PMOS we have. Now we need to connect the drain, and additionally we need to make an N well. We need to make body contacts. So we will do it. We'll start. So when we press P is making any path, and R for rectangle. Let's assume if I select metal 1, ME1, and if I press R, I can make a simple rectangle. Or I have an option of by using the same thing using pressing button P. So you can see that these are metal lines which I can draw for connecting one transistor with the other. So I will use P and I will click on the edge of this, the drain of this PMOS transistor. So now I will connect to the NMOS. Now you can see that output connection is done. We are done with this part. Now we need to connect the gate. So the gate is a poly layer. So if we click on the, if we put our mouse near the edge of this poly, we can connect, and further we can take it out like this. So the gates are shorted. You can see that the gates are also shorted. Now we will also, we can take out this out. Now we need to connect VDD to the source and ground to the source of NMOS. So again we'll press P to take this metal. Similarly we will take this. There is a good standard practice, like metal lines should be used with a single metal type. The direction, I would say the orientation. So vertical lines are for, if we set for metal 1, we can draw horizontal lines from with metal 2, and we can play with the width by pressing F3. Let's assume we use 0.5. So this is something we will use again, 0.5 here. So these metals are at different layers. So if you again see, the substrate is there on which we have these transistor. Metal connections are at different layers. For that, if you want to connect to that, we need a via, we need a connector. So if I want to connect, you can see that this is labeled as VDD, but this metal 2 is not labeled at VDD because it is in different layer. So to connect these two metal lines, we will press O. O is to add a via. You can see here it is in create via. So what we want to connect, we need to connect metal 1 to metal 2. And how many vias? Let's add 2 cross 2. So the moment we press this, you can see now the metal 2 is also labeled at VDD. What it means that this VDD is which was there in the source of this PMOS is connected to metal 1, and now it's connected to metal 2. Similarly, we'll add for our ground. So what is left? So let's try to do some, so in this, in all this design, there are 3 things we need to do for parasitic extraction for practical layout. One is DRC, second is LVS, and third is specs. If you can see this, if you want to start with LVS, this is exactly equivalent to our layout, is equivalent to our schematic. But if by mistake, if we don't connect some of those pins, so we need to have some way to find out like whether the schematic and layout is exactly same or not. So this is one-to-one matching. And design rule check is more into like it is a foundry related thing. Like if I tell you to draw a straight line, and if I tell you to draw two straight line very close to each other, so we have a limitation. Similarly, tool also have a limitation that it can make a, uh diffusion or any that square rectangle box. It cannot make whatever we want. It has a limitation. Like if you see a stepper motor of which can rotate at 1 degree, so that is the minimum what we can achieve. So these design rules comes from the foundry where our transistor will get manufactured. And third is the parasitics. Like all these you can see the poly lines. It will have its own resistance and a parasitics with ground. So these things, these three we will use these three uh, features. So now we'll start with DRC, design rule check. So it will see whether any rule is violated or not. So for now I will use, so we need to give only one rules. So whenever you start this layout, these rules is given to all. For me, I have kept in one folder UMC 180 rule files, and there is one DRC this. And yes, you need to run it. That's it. So it
Excuse
says
me.
that yes.
Can you just please explain the DRC part again? I don't get that. How can you get this DRC file and etc.?
Okay. DRC file is something which is provided by the foundry. So means actually, do you want to understand how DRC, what DRC does, or how we'll get that file?
Exactly what DRC does, because I just can't feel that necessity behind what is DRC and how to.
Okay. Fine. So I will explain just by completing this part. You can see that there are some errors in this options. After running DRC, there were some errors. One error was like that the maximum n plus diffusion to nearest p plus pickup spacing, it should be 20 micrometer. So this is the limit which we are getting from the foundry, that if you have one diffusion, so you need to have the nearest pickup should be within 20 micrometers. So these are the rules which are given by the foundry. So this is one rule. What I will do is I will intentionally create one more line uh, with metal 1 very close to it. So what is the difference? By pressing K, we can find out the difference. It is 0.04. So, and if you see the length, this is our length of K. So this is 180. So every unit is in microns. So it is 0.18 microns, the length of our transistor. And we have created one metal lines. The distance is just 0.04 microns. So what will happen if we run DRC? Means that can our foundry make these two lines such close or not? So this helps to find. Where is, yeah, we'll run DRC again. So it will pop up one error that there should be a minimum distance between these two lines.
Okay, so you mean the channel length that we are going to use in the transistors is going to be the minimum distance between any such metal plate or any such
Yes. These are the
object.
rules. So for you can see that for metal 1 to metal 1, the rules are like the spacing should be at least 0.24. Yani nanometer you should have a distance. If your length is, the length of your width is less than 10 micrometers. So these are the rules, standard rules, which has come from the foundry. It has the limitations of their instrument. That's it. How an instrument can draw two lines, two metal lines, or all of the thing. Whether you design, you make a diffusion or you make a via, everything has associated some rules. Which, because these things comes from the instruments what from which this transistor will be manufactured. So this was one of the rules. So now the only thing is to clear this rule is like don't have any line which is so much close. You can, to solve this problem, yes, you can see that if you know what is the minimum rule, you go ahead 0.25, 24. Yeah. So if you are here like this, so you won't find any error. So this is the limitation of this boundary. So what were the other errors? It was not directly mentioning like the error was due to the body contacts are not there. If you see, if you see this, we need for PMOS we need a well and a contact. Exactly, for NMOS we need a body contact. This is also missing, and the errors were because of that. So what we'll do, for body contacts, we have this, first we'll make a well. We need to put our PMOS inside a well. So you can find this NWell option is there. So first click on NWell and we'll make a rectangle in which we'll keep our PMOS. That's it. So now this boundary shows that we need to have end doping inside this bond in this area. And what else we need to do? We need to have, again, we need to make a body contact. So we'll go now, which body contact we want? M1 NWell. This is the thing which we want. If you can see here, this is NWell, and whatever connection we want from top, it will be metal one. So just by using that, we can put directly over here. So by putting this, what it did, we have from substrate, from well, we have a contact on metal one, and metal one is connected to VDD. So by this way, we are done with this part. Similarly, we don't need any well for our NMOS transistor. The whole substrate is our, you can say it's type of well, big well in which we have. We need to, here what we will select M1 and P diffusion. We have a P substrate. So now we are making our body contact. So we are done. So now if we do DRC, we will not have any error related to design rule. Let's run it and see it again. There are errors. It is more related to like the foundry asked that whenever you are using metal one, it should be, there are rules like it should cover the whole area of 33% of the chip. So let me see this error. ME1 metal one coverage must be larger than 30%. 25% if it is in small area. So these errors can be resolved at the top level. Like if we have inverters, if you have other different block, D flip-flops and many other blocks, later we can take all these block at the top level, and wherever space is left, we will put dummy metals to just resolve these errors. All these error can be resolved. You can see all are like in 50%, you have this much metal. So this is not related to design. It's like to have a balance, to don't have much stress on the fabrication process. We use this. Again, this is that diffusion in this area, 500 micrometer cross 500. We need a 20%. We need a diffusion. So what it is talking is, let me open the schematic, the layout. So we have added this connection, that diffusion to metal. These connections should be in every 250 cross 250 micrometer. We need to have 20% diffusion thing. So these are rules which Foundry gives, but what we have made is exactly equivalent to what we have on the screen in there on the right. So now we are done with the rules, but we need to have pins from where we'll get the connection. So we will make the pins. For pin, we need like P4 was path and control P is there to add a pin. We'll put label, and the label will dependent on which metal we are using. Suppose in this case we have this VDD which is on metal 2. So if you want to have a connection in schematic, we have used pin. The all the VDDs were connected to VDD pin. Similarly, we have, for that we need to select this CAD. M1 CAD is there. M1 CAD text here. So N1 CAD text. Again, we'll use same ground for, and for this poly we need PO1 CAD text. IoT. And for our out, so let's, for intentionally I'm deleting this so that when we'll do LVS, now we are interested in doing LVS, whether whatever we have made in schematic matches our layout or not. So there you can see that it is slight red, this part. So these part need some inputs. So again I have to give uh, the layout rule files. LVS and input. So whatever, so this is layout versus schematic. So for layout, everything will be extracted from layout view. For netlist schematic, it will extract it from schematic viewer. Just two things we need to do. We need to get rules and this export from schematic viewer and just run the LVS. So it should show one error because we have left one pin connection is not there. So it is showing that there is a discrepancy. So the number of ports in our source schematic was 4 and layout is 3. Nets are same, instance are same. So this type of error comes if we miss some label or if we miss some routing. So I will correct it. Now I will run it again. So we can see this green smiley. So now our layout and schematics are matched. The first thing is we need to see like we are not violating any rules of this layout, and second is layout versus schematic. Now the third and the last thing is we'll do some parasitic extraction, because in our schematic diagram, if we see, we have this transistor only, and you can see this nets are ideal connections. Now what will happen if in our case we have used poly to connect the two gates, this, so it will have its own resistors, this will have it, uh, it will be very small but it will be there. So in very high speed circuit, these parasitics will just limit our design, so we need to take care about, and we learn like how we can estimate like what is the parasitics in this specs analysis. We'll go to Calibal and run specs. We'll have one XRC. We have three DRC, one is LVS, and XRC for parasitic extraction. And that's it, run. So what it does, it calculates all parasitic based on the models we have. One thing which we left was in the output, we need to select caliber view. Now, actually, we also need to provide cell map. So in this cell map, all information are related to the foundry, like what parasitics to keep. So in the same, actually we need for all this process, we need 4 files, DRC, LVS, specs. These are for rules, and for mapping, like how much, for every trace, how much R is there, C is there. We need to provide that cell map file. We will just now see. So zero warning, zero errors. So if you see, there are two transistor was made, have come up, L180 nano and this with 2. This is our PMOS and this is our NMOS, and there are many parasitics, cap and resistors in the bottom. So these parasitics, resistors and caps are due to the metal layers and connections we have made. So this does our parasitic extraction. Now what, for when we did our schematic simulation, we have used only this transistor. Now with these parasitics, how our circuit will perform and how we'll do the simulation in just 5 minutes we'll see. So what is the advantage of parasitics extraction is, like in some very high speed design circuit, we need to restrict our parasitics also, because it will reduce the speed or bandwidth of the system. So there is one option called RVE. So after running PEX, you can find out that which two nodes, how much parasitics are there. So this helps in debugging or improving our. So if we can see, if we click on INP, so it gives like, so this is the resistor. There are 6 resistors uh, of these values, and if I double click on it, so you can we'll see in our layout. So it's not appearing. Highlight parasitics. Yeah. So this resistor is around 58 ohms. This, and here we have 85 for our. So so we can take care in laying out also. So that's it for extraction. So now we are done with all the 3D RC, LVS and PEX. Now we'll just simulate. So when we do those caliber PEX extraction, this caliber view has come. So this is our schematic view where we have used transistors and with ideal wires. We have layout view. You can see in the bottom schematic view, layout view, and we have caliber with parasitic. So again, we'll go to our inverter .pb, the test bench where we have simulated with the schematic. We'll load. So we have loaded our ADE. So now when we run this, so the schematic view has run. Since if so, how we can change to our parasitic extracted view? So what I will do, I will just save to just see the difference. So we have this for our schematic view. Now for our parasitic view, we need to go to setup, environment, and just add calibrate. So when we add calibrate, what it does, it will not take the spectre view. It will take the calibrate view. This is the switch view list. First, what it does, it finds the calibrate view and then it goes to spectre. So if it doesn't find calibrate view, then it will directly simulate the ideal one. Now we'll run it. Now you can see that whatever waveform we'll get, it will have some variations. This output. We'll remove the input because input are exactly the same. You can see there is a difference between the two. Because of the parasitic capacitors and resistor, there is a delay. You can see the green one is on. So this delay is because of those RCs. So just by removing this calibre, we can again, if you want our schematic level simulation, we will do it by this. This overlaps exactly with the first one. So that's it. We can take some questions if we have some more time. Anyone?
Yeah, actually, throughout these 3 days, what we got is kind of the views about the schematics, and then you just kind of notice about the PVT analysis, a little bit about noise analysis, and right now it is about layout. I actually just kind of feel that this total 3 days workshop is kind of totally rushed up thing, because I need to just kind of focus on these things quite elaborately, but still it's really better. Uh, would you please sum up like this one? If I just have one common source amplifier to be just almost set up and run, already running. So how like PVT analysis, noise analysis, layout, in which order should it be done?
Okay. See if okay, understood. So which order? So the first tutorial was more into like what are the tools, how we can analyze things. So that is the first part. So you need to know like how you can do AC DC. So the first two tutorials are more into like, yeah, layout is the last thing you will do. Analysis and layout. I would say like there are three things: analysis, design, and layout. Design and analysis both, you should know like how you will add things. So layout, it's I would say that all three are interrelated. So sometimes what happens is we do layout and find out that our non-ideality has increased due to some reason of parasitics of resistor capacitors. Then we go back into design. So mm, I think I have not properly answered it. But the way which industry does is they give you some problem, like they want to make, let's assume they want to make an amplifier with gain and bandwidth of some specification is given. Based on that specification, what you do, you design it on paper, like how much W by L sizes you will do. You do first schematic simulation, and when everything meets, you just then go to layout and then send it to fabrication, and then you will get your chip back. So it will be, yes, first schematic then layout. That will be the thing, and before sending to fab you need to do all those PVT analysis. Have
Okay,
I
so
cleared it?
yeah. It's quite better when you just totally elaborate it with about specifications. But one thing
Yes,
that
yes.
is, if in the case of PVT analysis, I find a little bit any kind of discrepancy, then I have to go back to the schematic again, right?
Yes, you need to tweak some of the parameters, like due to process variation or temperature variation, your transistor, some of the transistor may get out from saturation. So you need to tweak it such that in every corner. So yeah, it's a iterative process. Means you need to go from analysis, analyzing all your schematics, PVT, then it's a closed loop. Whenever you achieve all your performance, then only you start your layout. And even layout also come for if you're working in RF, very high frequency, that also comes into your loop. Sometimes people do schematic, PVT, layout, again they need to change in schematic, do all those process. This is how analog design is.
Okay, so it's quite rigorous process.
Sorry?
It's quite rigorous process, I feel so. Even with
Yes, yes.
this much of applications in Cadence, I
Yeah.
just didn't really expect Cadence to be this much user friendly. But yeah, as you showed us, that it's quite some beautiful
Yeah, for digital,
experience beginning.
there are very good tools available. We don't design anything from scratch like inverter, D flip-flop. Maybe for some small thing you need to do. There are some tools which does all the things. You need to give VHDL code and it will generate your layout. And it will take care all of your timing, like setup and hold violation, everything it will take care. So mainly for analog, it's a rigorous process we need to go through, and especially if you go to lower technology. What we have done, we did in 180 nanometer, but if you go to 65 or 28 nanometer, it's more challenging to design in that, considering all PVT variations. Because as your supply is reducing, your VDS is becoming very sensitive. All those parameters like GM, RO. So for low voltage design, you need to put more effort in design. So there are various. That's where very innovation comes. There are various design techniques. Can we make a circuit such that, like when you study negative feedback in op-amp designs, all those things, even if you have process variations, you will get a fixed gain because your gain is dependent on R1 by R2, like an inverting amplifier. So what we will do, we'll have a very high open loop gain and we'll use passive components. So there, so ratios, whenever you have ratio, R1, if R1 varies, R2 will also vary, so you will get a pretty good gain. So these are many design techniques are being used to take care all those variations. So it's not like you need to do it by tweaking always. Right.
Yeah. Just one thing at the end I would like to ask you that the videos will be available, right?
Yes, yes.
Because I don't know whether when actually uh, can we come back to the campus, but
Yeah.
after taking any kind of course which will again just make us make Cadence available to us. So in that
Yes, yes,
case,
yes. Yeah,
I
yeah.
feel that I need to just get back to these videos again.
Yeah, yeah, sure. We that video will be provided, and I would say like if you want to read more, there are various good IEEE papers on PVT invariant circuits.
Oh,
So you can study like people have done a lot of innovation in terms of designing circuit which is PVT invariant. Even with changing temperature, you won't find much change. So it totally depends on application. Even though there are specific circuits which is PVT invariant, you can go through
okay.
those. So that's it.
Thanks a lot for this session too.
Yeah, you can also will some feedback will be taken from the students, so you can give all your feedbacks so that next time it will be more better or what things can be improved.
Yeah, sure. Because as you know that this time Cadence is not kind of available to us as we are
Yes.
not in campus. So this
Yeah.
session was really kind of essential to kind of get a feel about what it's all about.
Yeah, anything, any positive and negative feedbacks, whatever there, so that that will be help us to improve all these sessions. Okay, we are done, I guess.
Hello,
Yeah,
hello.
hello. Yes.
There is one question in chat that how to get model files.
Okay, okay. So fine. Model files are given us. These files are generated by those foundries who fabricate these ICs. So you cannot get those model files as you cannot download in your PC. We need to remotely access to VLSI server, and we need to sign an NDA, non-disclosure agreement we need to sign. Like if we are getting access, I have also signed. Anyone from you, if you will use, you need to sign that agreement, like you will not disclose those model files, because there are various fabrication manufacturers are there, and you need to keep it preserved, like what are the VT values. In the model files you have all those informations, VT, mu, and how with process things will vary, how with temperature things will vary. So whenever you get a course, suppose if I think in CMOS you are not so it's very difficult to do remote logging. So if you join some MTech project, a PhD project in which you need to, if you are working on IC design, you will get that access from VLSI lab, and you cannot download anything in your PC or laptop. It's like I'm also accessing from VLSI lab server as I'm in campus. So because the line speed is pretty good, uh, I'm able to do it. Hope that answers.
Yeah, thank you.
Thanks a
Okay.
lot for this session.
Yeah,
Yeah.
there is one question like this tute is just for learning or will we also get to use Cadence? One thing honestly I will say that Cadence license are very costly, and we have very limited number of license. Right now I guess it's 40. So not all students can get access. Mainly those students who have taken the course will get permission to use, or if you are working in that area, if it is your research topic, your PhD or master's thesis, you will get access to Cadence. Yes, that's it.
Just another thing, as you said that only 40 number of people that can access this because of
Yeah, at a
license.
time
So,
40 can simulate.
oh,
Yes.
just at one point of time. Okay, okay, okay.
Yeah, one point of
That's
time. If
that's
suppose
fine.
41 person is there, he will need to wait till one simulation is completed among that 40.
Okay, okay.
So if the group is big, if the class is large, so what they do is they distribute time, they divide time so that one batch can work at different times.
I get.
Okay, we'll end.
Thank you, Miraj.
Yeah, thanks.
Yeah, thanks, Miraj.
Yeah, thank you.